Okay, so today we're going to look at one example. Before we look at example, just a freshman. So again, we are looking at one simple formula, which is F equal to KD. If you are if you are analyzing a single element, then you are using a small f, small k for the stiffness matrix, and small d for displacement. If you are analyzing assembly of a system, then you use a capital F for the force, capital K for the stiffness matrix, and small d for the displacement. Okay, so last lecture we have been going through a few examples and a few concepts which is important. Homogeneous boundary condition. We have two types of boundary condition. One is homogeneous, one is non-homogeneous. Homogeneous means that there is no displacement. There is no movement. So for example, your spring or your structure is inside a wall. So the boundary condition at that particular point cannot move. And then non-homogeneous means there's a movement there. There's a movement, there's a displacement value for that one. And also we've gone through a few examples. This is the one that we've been through last lecture. Assembly of spring in series. And then in this case, we have our boundary condition in point 1 and 2 is homogeneous. Then today we're going to look at one example, which is your tutorial question number 11. Yeah. So you're going to look at this system. So this system consists of a series of spring. Your point 1 is inside the wall, and your point number 5 is having some space here and is able to elongate. Yeah. So let me know if you're not able to see the PowerPoint slides or not able to hear me. Yeah. So just let me know. Okay. So let me check. Katana, you're here, right?
Yes, sir. Morning.
Okay, morning. Good. All right, we continue with our tutorial question number 11. Yeah. So we are having a combination of homogeneous boundary condition and non-homogeneous condition, or at point number 5. So the question asks us to find global stiffness matrix. Global, the word global means that you need to find the capital K, global, and the displacement of node 4, 2 to 4 means displacement from this point, this point, this point, and this 3 point, point number 2, 3, 4. And then we need to find the global nodal forces, means global nodal forces. We need to find the capital F. D is a local element forces. Local element forces means the small f, small f. So we need to look at global scale and also local scale. Node 1 is fixed, is here, while node 5 is given a fixed known displacement, which is 20 mm, which is here. The spring constant are all equal to K so and so. In this case, it's 200 kilonewton over meter. Yeah. So how do we solve? Yeah. So we tidy up the question a little bit. We solve for global stiffness matrix, and we still stay on the diagram that we have in your tutorial question number 11. So before start, you have to know the setup. So we have 1, 2, 3, 4, 4 spring, and then we have 5 node, 4 spring, and we have 5 node. Okay, and then we have external force at node number 5, which is labeled as F sub 5x. 5x, x means in the x direction. Yeah. And there's displacement at point number 5. Yeah. So we express each our stiffness matrix for element 1, 2, 3, 4 is the same, equal to 200 minus 200 minus 200 and 200. So if you don't understand this equation, go back to the previous slides where we derived the equation for individual spring. For the individual spring, where we have a two-node single element with two nodes. So this equation actually what we discussed in our early lecture. Okay, so first step is to express the stiffness matrix. This is a local stiffness matrix or individual element stiffness matrix. So K upper we have 1 means element 1, K2 element 2, 3, 4. Right? So why we can write like this? Because the statement let us know that all the springs constant is the same, 200. Of course, when it comes to exam, the K will be changes. Right? You won't have all the constant same. K will be different. So this is just an example. So the combination of homogeneous boundary condition and non-homogeneous boundary condition, then how you solve it. So first step is that when you have the elements in the matrix, then you put them into a global stiffness matrix. Means we use a superposition or superimpose method that we put into each individual location. Okay, so you put into this form. Yeah, so the step we already covered for in previous lecture. So so the first, again, you can use your pencil to break the matrix into their respective location. Yeah. So the first column will go to point 1. This is your U1. This is point number 2, U2, U3, U4, and U5. Same with this column also. U1, U2, U3, U4, and U5. Okay, so each one of it represent each one of it. For example, how you fill in this one is that for K element 1, you have 200 minus 200 minus 200 and 200. So this one represent this element. So this number represent U1, U2, okay, U1, U2. So that's why you put this element or this matrix into here. Okay. Why here you see 400? Because there's an overlapping of another matrix. Okay, here 400 means there's a 200 here, 200 plus 200, right? Because it's a combination. Yeah, this one K2 is because of K2, because your K2 matrix consists of U2. K2 means element 2. You are having node 2 and 3, so U2, U3, U2, U3. That's why you fill in the number here. That's why you have 400, 400 here. Then same, you put in the third element and fourth element. Okay. Any question for these slides? Any question for the superposition method? Anything that doesn't sound logic to you? Singy, is it okay for you? You understand?
Yes.
Okay, good. Right, we move to next slides. So this is when we have the global stiffness matrix, we put into a global equation, which consists of F equal to KD Again, be careful on the shape of the matrix that you use. F is a curly, K is a bracket, and D is this one. You expand this equation into the one. So just now you already get the global stiffness, and then the rest you just expand it. So for the force element, you have 1, 2, 3, 4, 5. So you have F1x, F2x, F3x, F4x, F5x. Displacement, you have 5 points. So you also have U1, U2 until U5. And then in this scenario, all our direction is in x direction, yeah. So that's why we use U. So maybe in exam or in your final exam, in your test. So I will give you. You need to be careful on the axis that I give you. So maybe I will just write y here. So all this you have to change to, if this is y, so all these have to change to v. If I change the question from, in this case is x-axis, but what happens if I change the question, the orientation become y-axis, then all the displacement here, you have to put v. If I change to z direction, you have to use w. Yeah. And of course, in exam, I won't write this one out. I will not write the phi x here. I'll just give you a value here. Yeah. So you have to know that this is represent external force at point number 5. Okay, so we put everything in the global matrix, in the force, this Stigma Metrics and displacement. Okay. Then we apply the boundary condition. Boundary condition, you have to be look at the diagram given. Boundary condition means you look at boundary condition. Basically, you look at two components. One is your force, external force, and the other one is your displacement, which is your d. It is your d. So from here, we the most easiest one is we start with displacement first. Yeah. So if you look at number 1, okay, Lai, what is the value of your U1? If you look at the diagram, what's the value of your U1?
$200.
U1. What is your U? What mean by U? What mean by this component? U1, 2, 3, 4, 5. What does it mean? What does it mean?
The displacement.
Displacement. So you look at U1. U1 means displacement at point number 1. So you look at point number 1. What is the value for point number 1? What is the displacement? 0, correct. How come just now you say 200? Where you see the 200? Okay, yeah, good. So point number 1 is 0. Okay, good. Like, okay. Katana, what is the value for U5? This one.
0, sir.
U5. 5. Point number 5. Point number 5. Huh?
Wait, we have like 2 points there, right?
I'm saying, looking at the spring. Yeah, there are 2 points, number 5 there, but we are focusing on spring. This point is just to confuse you.
I think it will have a figure.
Yeah, point number 5. How does it move or not move? Not moving.
It will move because there's a force.
It's free, right? It's free. It's free at this end.
Yeah.
And then with the force also. So what is the value? The value is given in the statement or in the question already. What is the value?
Wait. Oh, wait. Pardon. 20.0.
Yeah, 20.0. What is the unit?
This is millimeters.
Yeah. So you have to put in what unit?
Or in meters.
In meters. Why? Because our unit SI is meter and our stiffness matrix you see here on the screen here, your stiffness matrix is kilonewton over meter. So if you take something kilonewton over meter times mm, wrong answer, means that there's a breach of your mathematics calculation. The dimension is different, so all your calculation will be wrong. So here you will have 0.02 here, right, meter. Okay. The rest we need to find because the rest is the question asks us to find. So at least at early stage you know. Okay, now then Singy, what is the value of 5x here from the diagram? Do we know this? Do we given? Oh, 5 do not know. Sorry. Okay. All right. Okay. Once we have this global equation, we apply the bounding condition. Again, bounding condition. We look at the force and the displacement. We only have two things that we do not know here. Normally, the stiffness matrix it will be given. So we only have the force and the displacement. So like what all of you say. Okay. Right. So these two all of you already answered. Another hidden message in the question is that 0.234. If you look at 0.234, it's free to move, or we are applying the continuity principle, where if you pull at point number 5, point number 2 is following the movement, point number 3 is following the movement, point number 4 is free to move in x direction. If no resistant force at 0.234, again, there is no resistant force that stop number 2, 3, 4 from moving, meaning 2, 3, 4 is free to move, then the force at point number 2 will be 0. The force at point number 3 will be 0. The force at point number 4 is 0. So this is a hidden message. Okay. Singy, can you explain why we have value 0 for F2x, F3x, and F4x?
Because one is fixed, so 2 will follow. Because we pull at not 5, so 2, 3, 4 is just follow.
And okay, the main point is that why we put 0, because there's no resistant force here. Yeah, there's no resistant force at 0.234. Yeah, yeah. So again, the reason why we put 0 is because there's no resistant force. It's free to move. Okay, if the point is free to move, then you have 0, 0, 0 here. Okay, so again, this is a very famous question when it comes to exam. So if the point is free to move, the global force at that particular point is 0. Yeah. So again, yeah. So of course, in exam, there might be a section ask you why we assume value 0 to that particular point. For example, the question might ask you to explain why a certain value is assigned to global force at point number 2. Explain. Right. The question won't tell you is 0, but it asks you to explain why you use 0 at that particular point. Okay. Yeah, of course, if you answer force 2x equal to 100 means wrong already. That means you don't understand why we use 0 here. Yeah. So again, just a reminder. So you put in all the known value there. You just rearrange the matrix, all right, with the boundary condition. Okay, so 1x, f1x we don't know. There must be a force when you pull from point number 5. There must be something filled by point number 1. So there's a value for point number 1. And because point 2, 3, 4 is free to move, there's no resistant force. So that's why I put 0 at this component. K matrix we just copy, and then we put in the known displacement. So point number 1 is 0, and again point number 5 we need to convert into meter. Again, this is the error where students make mistakes most of the time. They just put in 20 here. Then the whole calculation was wrong already. Okay, so it will be waste all the effort after you calculate. So be careful on the unit. Yeah, because you are taking engineering courses, unit is very important. Okay, any question for the equation you see on your screen here? Any question you want to ask me?
Nope.
Okay, so again, in our class, don't try to copy all the numbers, because you can get all these numbers later on. Yeah, is try to understand the principle or the way we try to, the strategy we use to solve. That's more important. Yeah. Okay, so we move on. We have already solved for B already. Yeah. No, we already solved for A, and then now we have A already solved. Now B will try to solve for displacement for U2, 3, 4. Huh? Okay, we copy the equation we developed just now. Now we focus on the center. The center. We have 3 equations. All right, we have 3 equations. And we have 3 unknowns, so we can solve. This is a simultaneous equation solving strategy or steps. So again, how you get the first equation? You take the first number here, equal to the first row of your matrix times your another matrix here. Okay, so 0. I write out the first equation. You take 200 minus 200 times the first one. Of course, this is the first one is 0. This one have to match with the first one, so 0 plus, take the 400 times the second one, so you get 400 U2. Take the third one, negative 200 U3. Take this one times this one, 0, 0. This one 0 times this one 0. So the first equation gives you 0. Sorry, first equation gives you 0 equal 400 U2 minus 200 U3, and then you do for the same for the rest. Yeah. So you do for the third row here, to this one, and then do for this one. Then you'll get 3 equations. Then you solve for simultaneous equation. Okay. Another one is there's a side note there where I put your Hooke's law. Recall Hooke's law that you learned in your spring chapter. If you have a spring, how you find the spring force? F equal to kx, right? Or k delta. So at point number 5, actually you can calculate. So point number 5, you take k times the displacement of the spring or the elongation of the spring. So f phi x here equal to k delta. K is given, delta is given. So Fkx equal to 4 kilonewton. Lai, are you able to calculate, or do you understand why we get 4 Newton here? 4 kilonewton here?
Oh, yes.
Okay, good. Then, okay. The next one is that this is just one of the solution. So this one is that we're looking at force number 4, which is here, and then you get equation for this one, right? You get equation for this is F4. Then you focus on this row times this column. So you'll get 0 times 0, you get 0. 0 times U2, you get 0. Negative 200 times U3, you get this one. Oh, there's one more 0 here. Apologize for typo error. And then 400 times U4 and negative 200 times 0.02. So you get the first one and so on, yeah? Yeah. Okay. So this is one example where you focus on one of the component here. Yeah. So this is how you get the 4K kilonewton here. Yeah. Okay. So although in this 5 forces global matrix here we put 0, but when we focus on this equation alone, point number 4, if you expand it, we will we can only focus on this region. Means why we focus on this region? Because it's a overlapping of your U2, U3, and U4. Yeah, it's U1 and U5. So we want to solve U2, 3, 4. So we focus on this region, and then we will rearrange the matrix that we develop. So from the global matrix over here, you transform it only focusing on U2, U3, 4 component. So okay, this slide is to explain why we suddenly have a 4K Newton here. Yeah, when we only focusing on the matrix equation for U3, 4 component. Yeah, so be careful when you try to export the data from matrix. Don't straight away export 0 here. There might be a value in your F component over on the left hand side. Yeah, this is just a demonstration to remind you, don't direct copy 0 into your answer. If you direct copy 0 in the answer when you try to solve, then it's wrong. So this is try to remind you, you have to solve all the equation first. I mean, you try to write out the equation for that particular section For example, f for x here, this equation, when you expand, there is an equation when you put into a matrix of U2, U3, U4 matrix setup here. Okay, there's a 4kn in a f component. Yeah. Okay. So what does this matrix mean? It means that you're only focusing on this section. You just cut off this section and then you investigate what happened in this section. Yeah. On the left, this one, a big matrix here, you look at the bigger picture, 0.1, 2, 3, 4, 5. However, when you only looking at 0.2, 3, 4, you need to be careful. Yeah. Okay. We move on. So we solve this equation. When we solve this equation, we're able to find the displacement for point number 2, 3, and 4. Because this matrix alone on the screen, lower right corner of the screen here, if you put in the equation, for example, 0 equal to 400 times U2 plus negative 200 U3 plus 0, you get one equation, and then so on. Then you're able to solve the equation. Yeah, you do substitution and solve simultaneous equation. Then you solve for, then you'll get U2 equal to 0.005, U3 0.01, U4 equal to 0.015. Okay, try to understand the strategy that we're doing here, the solving question strategy. And this is just a reference answer. Yeah, it's just a reference answer. Okay, we move on. Point number 3, section C, we need to find the global nodal force. So you write back. So after you find your U2, U3, U4, you again write back the global matrix that you have just now. You substitute all the value there inside here, right? So now you have your K and D matrix, which is the stiffness matrix, and displacement matrix is complete already. So since you already have the complete K and D, you're able to solve for your F1 and F5. Yeah, you're able to solve. Because here you have 5 equations, you only need to find 2 unknown. So it's more than enough. Okay. So this is just a sample of calculation. So how you get the first one? You take the first row times first column. 200 times 0, get 0. Negative 200 times 0.05, you get this one. And then the rest 0. 0 times this one, 0, 0, 0. Second equation, take the second row. Second row times column. 200 times 0, you get 0. 400 times 0.05, you get this one. Negative 200 times 0.01, you get this one. 0 times this one, 0. 0 times this one, 0. You repeat for the rest, you'll get the similar equation that we see on the screen here. And when you do your calculation in the exam, how you check your answer is correct? All the force must be 0. Your system must be in equilibrium status, where if you add all the force together, you'll get 0. So from here, on the screen here, you see that if you add negative 1, 0, 0, 0, 1, your total force will get 0. This is how you check your system or your calculation whether correct or not. Okay, so in final exam or in your test later on, have your own self-check before before you submit your answer, make sure all the force inside your spring system is 0. This is to self-check. If you calculate the force is not balanced, means something wrong in your calculation. Yeah. Okay, any question for section C? Any question you want to ask me? Anything that doesn't make sense to you, or you don't understand why suddenly that particular number come up?
Sir, we just found F5x to be 4 kilonewtons, right? With the formula for springs.
Oh, you mean this one?
Yes.
You mean point number 5? Now, point number 5 just give you a general idea what is happening at point number 5. Yeah. So let me see here. Okay. Yeah, so point number 5 here is an external force, correct? The value is 4 kilonewton. However, these forces was distributed into the body. This equation is to show you that 5 kilonewton is what applied to point number 5. This is on okay, maybe I need to focus on the if you look at section C, it asks you to find the global nodal force. It means you focus on this point, rather than external force. It means all the number you calculate here is what happened in the point here. Okay. Global nodal forces. Okay. Do I answer your question, Katana?
Yes, sir. The 4 kilonewtons is the like.
It's the external. It's the external force. Yeah. It's not a nodal forces. So section C asks you about the nodal forces. Yeah. Okay. Now we look at section D. So when you put inside all the value you find here, then you look at section D is that to investigate the local element forces. Means you look at this matrix and then you try to find what is the forces. Right, again, this matrix that you find is a capital F, capital K, and D. We want to find small f now. We want to find small f, K, and D. So these are the steps. Yeah? So you look at element 1. We take out element 1. So you look at the matrix, you look for element 1. So element 1 give you only 2 points. This element 1, point 1 and point 2, or not 1, not 2. So in the matrix here, the one that represent element 1 is the one that I highlight on the screen here. Right. The dotted box here is just to highlight you the zone that you should focus on, because this is the U1 and U2. So the intersection of your displacement and your stiffness matrix is the one that you should focus on. Yeah, the data we are looking on. So you pull out the data from your matrix, then you modify a little bit. This becomes small f. So you write small f. 1 means refer to element 1, and then this one is 1x. This one 1x means point number 1 in x direction. F2x means point number 2 or node number 2 in x direction, and again we are looking at element 1, and you pull the matrix from the global matrix here, and the displacement also you copy. So again, here you have two equations, you have two unknown, you can solve. Here, this is just a simultaneous equation solution. Okay, so again, textbook answer I give you on the screen here. So if you solve simultaneous equation, you will get the first one, F1x element 1 equal to -1 kilonewton. F2x equal to 1, because this is it should agree with what we find just now. Yeah. Okay. So this for element 1. Okay. Stop me if you have any question or anything that you are not clear. Yeah. So again, the answer you can get from my slides, PowerPoint slide later on. Yeah. You can find all these answer. So during the lecture, at least you understand what is happening or what we're trying to do. Yeah. Okay. Then we move on to element 2. So element 2 again. Element 2, you're only seeing point number 3 and 2 and 3. Element 2, you have node 2 and node 3. So again, you go to the your global matrix. So you focus on the intersection point of your U2 and U3. So you get the one that I highlight on the screen here. You get the 400, 200, and 200 here. So of course, you have to be careful. The value 200 here, 400 here is a combination of two matrices. So when you copy into element 2, be careful. This value is not 400, it's 200. Because why? The K matrix for the K value for element 2 is 200, it's not 400. You see 400 here because it's overlapping because we do superimpose just now. Okay. Lai, do you understand why we get 200 here? Why we do not use the 400? Do you understand?
Not really know that.
Okay, so you don't understand. Singi, you able to explain why we use 200 here and not 400? Are you able to explain?
I'm a bit confused.
Confused? Okay. You understand? Okay, Singi, do you understand why we get 400 here?
Yes.
Okay. Because here is... Okay, let me... Okay, this is element 1. You have 200, negative 200, negative 200, 200. This is element 1. And when you overlapping with element 2, you have 200 here, 200 here, 100, 200, negative, negative. So if you look at element, we are now looking at element dimension. We only look at element 2 only. So we have 200, negative 200, negative 200, 200. This is element 2. We only break it into that particular element. Lai, do you understand now?
Okay.
Singi, do you understand?
Yes.
Okay, Katana, you're right?
Okay, sir.
Okay, good. So because on the screen here, the global matrix here is global, means is you combine everything. You combine everything already. But now in section D, we look at local element force, means we only look at what happens if you break the system into a small system when you only look at element 2, where you only have node 2 and node 3. So you just call back what we learned when we derive the equation F equal to KD for individual element. All right. So here we have F1, F2, for example, equal to K minus K minus K, K, and your displacement. U1, U2, for example. Okay. All right. Then you solve the simultaneous equation. You get force at point number 2 equal to negative 1.0 kilonewton and F3 equal to 1. So this you solve for second element. You do for the same for element 3 and 4, you will still get the answer. Yeah. So the rest of the slide is just repeat what we solve, what we do for element 1 and 2. You do it for the same. Element 3, same. Again, you look for the overlapping of the row and column. So again, in global matrix here, you have U1, U2, U3, U4, U5. If you break into their location, then here also same, U1, U2, U3, U4, U5. So overlapping of the location is the one I highlight with the blue color. Copy, again, when you copy, be careful. Don't copy 400 because again, it's overlapping of two matrices just now. It's overlapping of this matrix and this matrix. So it's element 2 matrix overlapping with element 3. So you have 200 plus 200 here. 200. Okay, yeah. So when you copy, be careful not to copy the 400. You have to break into 200. Okay. Okay. Then again, you solve the simultaneous equation. You'll get force at node 3 equal to so and so, node 4 so and so. So again, this value is for element 3, string number 3. And look at string number 3, you have 0.3 and 0.4. You do it for the same for element 4. Again, you look at this section, element 4. Yes. Anything? Go ahead.
I'm seeing most of the values are similar to the forces at the nodes. Is it possible like to use the node forces to find the forces at the element level?
You can, but I'm showing you the more easier way, because this one everything you extract from the global matrix here. Yeah, because later later on you will see a more complex system. This is just a series system. So if you look at your question 12 in the tutorial, then you need to be careful a little bit in your calculation. Yeah.
Okay.
Yeah. So if you look at element 4, repeat the same, you'll get the same. Again, there's a 200 here rather than 400. Yeah. So don't copy 400. It's overlapping of a matrix here. That's why you get 400. So when you solve the simultaneous equation for element 4, you get 4fx element 4 equal to -1 and 1 here. Yeah. Yeah. So this is how you solve for question number 11. Yeah. So again, I think most of you confuse how to get these Stigma metrics here. So again, if you write your K1 matrix or element 1 matrix, again, element 1 is referring to element 1, point 1 and point 2. So your stiffness matrix is U1, U2, U1, U2. The matrix will be, because the stiffness matrix is 200, so you have 200 here, -200, 200, and -200. Then you repeat for K2, element 2. So element 2, you look at the diagram, you have point 2 and 3. So what happened in your stiffness matrix for the element is U2 and U3 value. So although the magnitude is the same, although the number you see is 200 minus 200, but the value is represent different node. Yeah, is represent different node. Although every of the matrix here is 200, -200, -200, 200, but all the value, if you look at individual stiffness matrix here, it represent different node. This 200 on the left here is different from 200 at the left here. Okay. And then I repeat the same. If I write element number 3, element number 3 is this one. So we looking at 3 and 4. So when you write stiffness matrix 200, -200, -200, and 200, the value of 200 here represent node number 3 and node number 4. Node number 3, node number 4. So although all this number 200 here on the left, top left of the matrix is 200, but each of the number here represent different node. Then I write another one. Fourth element. Same. Here, node 4, node 5, node 4, node 5. Although the number here is still the same. 200 minus 200 minus 200 and 200. So when you superimpose all these into one global matrix, so you write the number, you write in the code. So you fill in the blank. So let's say you don't have all the number here. So how do you know the number of this one? Okay, maybe I use a different color. Okay, the first one I use red color to represent the first one. So the first one, I will get 200 here. Then I copy the second matrix. I change it to green. So green color represents the second matrix. So second matrix is U3, U3. So where is the location of U2, U3 is here. Inside the global matrix. This is U2, U3, U2, U3. So you copy 200 here. Negative 200, negative 200, and then 200 is here. So that's why here you will see 400. Okay, I continue with the next one. I use the purple color for element 3. So element 3, the matrix here, individual one is U3 and U4. Why U3, U4? You look at element 3, is point number 3 and 4. So you go to the global matrix, you look for the U3, U4 only. So where is the U3, U4? Is this one and this one. So is here. This location. So you copy the number U3, U3. So U3, U3. So you get 200. Then this is negative 200, negative 200, and 200 here. Then you repeat for element number 4. I change to red color again. So element number 4 is element number 4. You have 0.4 and 0.5. So U4, U5. So you look for U4 and U5. So it's the overlapping of this section. You just put in the coordinate. So U4, 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 U4. For fourth element, you use red color pen. So 200. And then this one negative 200, negative 200, 200. So that's why this location you will see 400. This location you see 400. This location 400. Okay. So when we look at individual element later on, you only look at this small square that I draw on the screen here. Singy, do I explain your question just now?
Yes.
Okay. Lai, you understand now?
Yes.
Okay, Katana, any question you want to ask me on this one?
No, sir.
Okay, good. All right. Before we go for a break. Okay, just for the record. So for your tutorial question number 12, I'll let you go through my slides later on. Yeah, you go and read my slides. So let me stop the recording.